sklearn kernel approximation. Description kernel approximation methods are used to approximate the nonlinear mapping of data into a higher dimensional feature space that is often used in kernel methods like support vector machines SVMs. This approximation makes it possible to use kernel methods efficiently on large data sets. Inputs X the training data. Typically a 2D array where rows represent samples and columns represent features. Y the target values for supervised learning problems, or none for unsupervised learning. Outputs approximated feature representation, a transformed version of the input data. Typically a 2D array with a higher number of features than the original data. Model object the trained kernel approximation model that can be used to transform new data. Steps feature mapping. The kernel approximation method uses a predefined function, e.g., a random Fourier feature mapping to map the original data into a higher dimensional space. Approximation the method then approximates the kernel function which measures similarity between data points in this higher dimensional space, typically using random projections or other techniques. Metrics accuracy the performance of the model on the task, e.g., classification or regression using the approximated features. Efficiency the computational time and memory usage of the kernel approximation method compared to the original kernel method. Visualization plots scatter plot visualization of the original data and the approximated feature representation. To understand how the method transforms the data. Feature importance plots showing the importance of different features in the approximated representation. Fine-tune parameters. Gamma controls the width of the kernel function, influencing the level of nonlinearity. Number of features determines the dimensionality of the approximated feature space. Uncertainty methods. Ensemble methods using multiple kernel approximation models with different random seeds to estimate the uncertainty in the predictions. Bayesian methods incorporating prior knowledge about the data to derive probabilistic predictions. And uncertainties. Challenges and fixes. Challenge 1 loss of information due to approximation. The kernel approximation may lose some information from the original data, leading to reduced accuracy. Sample use case that resulted in challenge 1 using kernel approximation for image classification, where subtle features are important. Fixes to challenge 1. Increase the number of features in the approximated representation. Use a more sophisticated kernel approximation method. Employ feature engineering techniques to capture important features before applying kernel approximation. Challenge 2. Computational overhead. Kernel approximation can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 2. Training a kernel SVM with kernel approximation on a large dataset of text documents. Fixes to challenge 2. Optimize the implementation of the kernel approximation method. Use parallel computing techniques to distribute the computation. Consider using a more efficient kernel approximation method, such as Nystrom approximation. sklearn kernel approximation additive Chi2 sampler. Description: the additive Chi2 sampler class implements a kernel approximation method for efficiently approximating the chi-squared kernel in high-dimensional spaces. The chi-squared kernel is a popular choice for measuring similarities between histograms or other non-negative data. The additive Chi2 sampler approximates the chi-squared kernel by using a sum of random Fourier features, where each feature is generated by sampling from a distribution related to the chi-squared distribution. Inputs: X the input data, which should be a 2D array of shape n samples. N features where each row represents a sample and each column represents a feature. The data should be non-negative. Sample weights optional array of sample weights, which should have the same length as the number of samples in X. If provided, the weights are used to adjust the importance of each sample during the sampling process. Outputs. The output of the transform method is a 2D array of shape n samples. N components where each row represents a sample and each column represents a random Fourier feature. Steps. The class takes the input data X and the desired number of components n components as input. It then generates n components random Fourier features by sampling from a distribution related to the chi-squared distribution. For each input sample, it calculates the value of each random Fourier feature by applying a function e.g. sine or cosine to the dot product between the sample and the feature. Finally, it returns the array of random Fourier features. Metrics. Accuracy measures the closeness of the approximation to the original chi-squared kernel. Runtime measures the time taken to transform the input data. Visualization plots. Scatter plot of the original data and the transformed data to visualize the mapping induced by the approximation. Histogram of the random Fourier features to visualize their distribution. Fine-tune parameters. N components the number of random Fourier features to generate. Higher values lead to better approximation accuracy but also increased computational cost. Sample weights assigned to each sample during sampling. Uncertainty methods. Bootstrap use resampling to estimate the variability in the approximation. Bayesian methods introduce prior distributions over the parameters of the approximation model and use Bayesian inference to estimate the uncertainty. Challenges and fixes. Challenge 1: choosing the optimal number of components. Sample use case that resulted in challenge 1 using a small number of components can lead to poor approximation accuracy, while using a large number of components can be computationally expensive. Fixes to challenge 1: experiment with different values of n components and evaluate the trade-off between accuracy and runtime. Consider using cross-validation to select the optimal value. Challenge 2: handling high-dimensional data. Sample use case that resulted in challenge 2: the runtime of the approximation can become prohibitively long for very high-dimensional data. Fixes to challenge 2: consider dimensionality reduction techniques such as PCA or feature selection. Before applying the approximation, investigate alternative kernel approximation methods that are more efficient for high-dimensional data. sklearn kernel approximation Nystrom. Description: the Nystrom method is a technique for approximating a kernel matrix, which is a representation of the similarity between data points. It achieves this by selecting a subset of the data points called landmarks and computing the kernel matrix between the landmarks and the entire dataset. This smaller kernel matrix is then used to approximate the full kernel matrix. This is particularly useful in high-dimensional datasets where calculating the full kernel matrix can be computationally expensive. Inputs. X: this is the input data. Typically a 2D NumPy array where each row represents a data point. Kernel: this defines the kernel function to be used. It can be a string specifying a built-in kernel like RBF, linear, poly, or a callable function defining a custom kernel. N components: this determines the number of landmarks to be selected. A higher value leads to a better approximation but also increases the computational cost. Outputs. Feature map: this is the approximated feature map. A 2D NumPy array representing the data points in the lower dimensional space. Each row corresponds to a data point, and each column represents a dimension in the lower dimensional space. Kernel matrix. This is the approximated kernel matrix, a 2D NumPy array where each element represents the similarity between two data points in the original space. Steps: randomly select a subset of data points landmarks from the input data. Compute the kernel matrix between the landmarks and the entire dataset. Use the kernel matrix and the selected landmarks to construct an approximate feature map for each data point. Metrics: accuracy. Evaluate the performance of the Nystrom method in approximating the kernel matrix. This can be assessed by comparing the approximated kernel matrix with the full kernel matrix if feasible, using metrics like mean squared error. Computational efficiency: measure the time taken to compute the approximate feature map using the Nystrom method compared to the time taken to compute the full kernel matrix. Visualization plots. Kernel matrix visualization. Plot the original and approximated kernel matrices to visually assess the quality of the approximation. Feature map visualization. If the dimensionality of the feature map is low enough, a scatter plot can be used to visualize the data points in the lower dimensional space generated by the Nystrom method. Fine-tune parameters. N components, the number of landmarks. Increasing this value improves accuracy but increases computational cost. Gamma for RBF kernels. This controls the width of the Gaussian function. A smaller gamma results in a narrower Gaussian, emphasizing closer neighbors. Uncertainty methods. Monte Carlo dropout. Train multiple Nystrom models with different random landmark selections and average their predictions to get an estimate of uncertainty. Bayesian kernel learning. Use a Bayesian approach to model uncertainty in the kernel parameters. Challenges and fixes. Challenge 1. The Nystrom method can be sensitive to the choice of landmarks. Poor selection can lead to a poor approximation. Sample use case that resulted in challenge 1: using a small number of landmarks for a dataset with complex structure. Fixes to challenge 1. Increase the number of landmarks. Use a more sophisticated landmark selection method, such as k-means clustering. Perform multiple runs with different random landmark selections and average the results. Challenge 2. The Nystrom method can be computationally expensive for large datasets. Sample use case that resulted in challenge 2: using a large dataset with many data points. Fixes to challenge 2. Use a smaller number of landmarks. Use a faster kernel function, such as the linear kernel. Use a parallel computing framework to speed up the computation. sklearn kernel approximation polynomial count sketch. Description: the polynomial count sketch class implements a feature map for approximating polynomial kernels with a count sketch. It is a randomized algorithm that uses a set of random projections to map the data into a lower dimensional space while preserving the pairwise dot products between the data points. Inputs: X. This is the input data, which can be a NumPy array or a pandas data frame. It represents the data points that will be transformed using the polynomial count sketch feature map. Degree: this parameter defines the degree of the polynomial kernel that the feature map is approximating. Higher degrees lead to more complex feature maps and potentially better kernel approximations, but also increase computational cost. Gamma: this parameter controls the scaling factor for the polynomial kernel. It scales the dot product of the input data before the polynomial function is applied. Random state: this parameter controls the randomness of the feature map construction. By setting a specific value, You ensure that the same set of random projections are used every time you instantiate the polynomial count sketch object, which helps with reproducibility. Outputs. Transform. This output is the transformed data after applying the polynomial count sketch feature map to the input data. It is a NumPy array with the same number of rows as the input data but with a different number of columns. The transformed data can be used for various machine learning tasks like classification or regression. Fit. This output returns a fitted polynomial count sketch object. This object contains the random projections used for transforming the data, which can be reused for transforming new data points using the same feature map. Steps. The polynomial count sketch algorithm first generates a set of random projections. These projections are used to transform the input data into a lower dimensional space. Then, it applies the polynomial function to the dot product of the transformed data. This step introduces nonlinearity into the feature representation, capturing potential nonlinear relationships in the data. Finally, the output is a set of features that approximate the original polynomial kernel applied to the input data. Metrics. Accuracy. This metric can be used to evaluate the performance of the polynomial count sketch feature map for classification tasks. It measures the proportion of correctly classified data points. Mean squared error (MSE). This metric can be used to evaluate the performance of the polynomial count sketch feature map for regression tasks. It measures the average squared difference between the predicted and actual values. Visualization plots. Scatter plot. This plot can be used to visualize the transformed data after applying the polynomial count sketch feature map. It can help to understand the distribution of the transformed data and how the feature map affects the data representation. Heat map. This plot can be used to visualize the pairwise dot products of the transformed data. It can help to understand how the feature map preserves the pairwise relationships in the data. Fine-tune parameters. Degree. This parameter controls the complexity of the feature map. A higher degree leads to a more complex feature map, potentially capturing more complex relationships in the data, but also increasing the computational cost. Gamma. This parameter controls the scaling factor for the polynomial kernel. It affects the magnitude of the dot product of the input data before the polynomial function is applied. Random state. This parameter can be used to set a specific seed for the random number generator used by the polynomial count sketch algorithm. This ensures reproducibility of the results. Uncertainty methods. Bootstrapping. This method can be used to estimate the uncertainty in the polynomial count sketch feature map by repeatedly sampling with replacement from the original data and generating multiple sets of random projections. Bayesian inference. This method can be used to model the uncertainty in the polynomial count sketch feature map by incorporating prior knowledge about the data and the feature map into a Bayesian framework. Challenges and fixes. Challenge 1. High dimensionality of the transformed data. The polynomial count sketch feature map can lead to high dimensional data, especially for high degrees of the polynomial kernel. This can increase computational cost and potentially lead to overfitting. Sample use case that resulted in challenge 1 using a high degree of the polynomial kernel for a dataset with many features. Fixes to challenge 1 use techniques like dimensionality reduction to reduce the number of features in the transformed data. Consider using a lower degree for the polynomial kernel. Challenge 2. Memory constraints. The polynomial count sketch feature map can require significant memory to store the random projections. This can be a challenge for datasets with many features or a high degree of the polynomial kernel. Sample use case that resulted in challenge 2 working with a very large dataset with many features and a high degree of the polynomial kernel. Fixes to challenge 2 use techniques like out-of-core processing to handle the data in smaller chunks and reduce memory usage. Consider using a lower degree for the polynomial kernel. sklearn, kernel approximation, RBF sampler. Description: RBF sampler is a class in scikit-learn that approximates the feature map of a radial basis function. RBF kernel using a random Fourier feature RFF method. This method enables the use of kernels in linear models, accelerating the training process and reducing memory consumption compared to directly using the kernel. Inputs: gamma a float, specifying the width of the RBF kernel. It controls the smoothness of the resulting features, with larger values leading to smoother features. N components an integer, representing the number of random features to generate. This determines the dimensionality of the transformed feature space. Higher values usually lead to a better approximation but increase computational cost. Random state an integer or none, used for reproducibility of the random feature generation. If none, the random number generator is initialized using the current system time. Outputs: transform X applies the RBF approximation to the input data X, returning the transformed features. X can be a NumPy array or a sparse matrix. Steps: generate random vectors. The RBF sampler generates n components random vectors from a Gaussian distribution with 0 mean and variance equal to 1 to gamma 2. Calculate inner products for each data point in X. Compute the inner product between it and the generated random vectors. Apply cosine function. Apply the cosine function to the inner products and multiply by the square root of 2n components. This results in the approximate feature representation. Metrics: approximation quality. The quality of the approximation can be evaluated by comparing the performance of a linear model trained on the approximated features to the performance of a kernel model trained on the original data. Computational time: the time required to generate the approximate features is usually significantly lower than the time required to calculate the kernel matrix for the original data. Visualization plots: feature distribution. Plotting the distribution of the generated features can help visualize the effect of gamma and n components on the feature space. Performance comparison. Plotting the performance of a linear model trained on the approximated features against the performance of a kernel model on the original data can help assess the approximation quality. Fine-tune parameters. Gamma adjusting. Gamma can control the smoothness of the resulting features. A smaller gamma leads to more localized features, while a larger gamma leads to smoother features. N components. Increasing n components generally leads to a better approximation but increases computational time and memory consumption. Uncertainty methods. Confidence intervals. Confidence intervals for the approximated features can be obtained by applying standard statistical techniques to the random feature generation process. Bayesian methods. Bayesian methods can be used to model the uncertainty in the approximation process and obtain posterior distributions for the generated features. Challenges and fixes. Challenge 1: overfitting. If the number of random features is too low, the model might overfit to the training data, leading to poor generalization performance. Sample use case: using a small value of n components, the model might achieve high accuracy on the training set but fail to perform well on unseen data. Fixes: increasing the value of n components to reduce the risk of overfitting. Challenge 2: computational cost. Generating a large number of random features can be Computationally expensive, especially for large datasets. Sample use case when dealing with millions of data points. Generating a large number of random features may take a long time. Fixes using a smaller value of n components or exploring techniques like subsampling or mini-batching to reduce the computational cost. sklearn kernel approximation skewed Chi2 sampler. Description: skewed Chi2 sampler is a kernel approximation method in scikit-learn that approximates the feature map of a chi-squared kernel. This method is particularly effective for high-dimensional sparse data, common in text and image data. The chi-squared kernel is a popular choice for such data as it captures the similarity between features based on their occurrences. Inputs. X. This is the input data, typically a sparse matrix representing features, with each row corresponding to a data point and each column to a feature. N components. This parameter specifies the number of components in the approximate feature map. It controls the dimensionality of the transformed data. Higher values generally lead to better accuracy but also increase computational cost. Outputs. X new. This is the transformed data, which represents the approximated feature map for the input data. Each row in X new represents the transformed feature vector for the corresponding row in the original input data X. Steps. Feature extraction. The skewed Chi2 sampler extracts a set of features from the input data X, which are used to approximate the feature map of the chi-squared kernel. Feature transformation. The extracted features are then transformed using a specific mathematical function, which approximates the chi-squared kernel function. Metrics. Accuracy. This measures how well the approximated feature map captures the similarity between data points compared to the actual chi-squared kernel. Computational cost. This measures the time and memory resources required to perform a transformation. Visualization plots. Scatter plot. This visualizes the transformed data points in a 2D or 3D space, which allows for visual inspection of the data distribution and the effectiveness of a approximation. Fine-tune parameters. N components. This parameter directly controls the dimensionality of the transformed data. Increasing N components generally improves accuracy but also increases computational cost. Uncertainty methods. Ensemble methods using multiple skewed Chi2 samplers with different random seeds can help estimate the uncertainty in the approximation. Challenges and fixes. Challenge 1. Overfitting. If N components is too high, the model might overfit to the training data, leading to poor performance on unseen data. Sample use case that resulted in challenge 1 using a high N components value for a dataset with a small number of training samples might lead to overfitting. Fixes to challenge 1. Consider reducing N components or using techniques like cross-validation to avoid overfitting. Challenge 2. Computational cost for very high-dimensional datasets. The transformation process can be computationally expensive, especially with large N components. Sample use case that resulted in challenge 2. Applying skewed Chi2 sampler to a large dataset with millions of features and a high N components value could result in significant computational overhead. Fixes to challenge 2. Consider using a smaller N components value or exploring alternative kernel approximation methods with lower computational cost. sklearn kernel ridge. Description: kernel ridge regression is a powerful nonlinear regression method that utilizes kernel functions to map data into higher dimensional spaces, enabling the discovery of complex relationships between features and target variables. It leverages a combination of linear regression and kernel functions to build a model that can handle nonlinear data effectively. Inputs. X. This is the input feature matrix, where each row represents a sample and each column represents a feature. Y. This is the target vector containing the values corresponding to each sample in the input matrix. Outputs. Self. The fitted kernel ridge model object. YPRED. This is the predicted target vector, calculated by applying the fitted model to new input data. Steps. Initialization. The algorithm initializes with a kernel function, which defines the similarity between data points. Common kernel functions include the linear kernel, polynomial kernel, and radial basis function RBF kernel. Feature mapping. The kernel function maps the input data into a higher dimensional space, creating nonlinear relationships that linear regression alone cannot capture. Regularization. A regularization term alpha parameter is added to the loss function to prevent overfitting and promote generalization to unseen data. Model training. The algorithm optimizes the model parameters by minimizing the regularized loss function. This involves finding the optimal weights for the linear regression model in the transformed feature space. Prediction. Once the model is trained, it can be used to predict target values for new input data by applying the learned weights and pay kernel function to the new input samples. Metrics. Mean squared error. MSE measures the average squared difference between predicted and actual target values. Lower MSE indicates better model performance. R squared. R indicates the proportion of variance in the target variable explained by the model. Higher R values suggest a better fit. Visualization plots. Scatter plot of predicted vs. actual values visualizes the model's prediction accuracy by comparing predicted and true values. Residual plot shows the difference between predicted and actual values, allowing identification of patterns or systematic errors. Fine-tune parameters. Alpha regularization parameter that controls the strength of regularization. Higher alpha values lead to stronger regularization and prevent overfitting. Kernel choice of kernel function, such as linear, polynomial, or RBF, determines the type of nonlinear relationship the model can capture. Gamma parameter for the RBF kernel that controls the width of the Gaussian function, influencing the smoothness of the decision boundary. Degree parameter for the polynomial kernel that determines the degree of the polynomial function, controlling the complexity of the decision boundary. Uncertainty methods. Confidence intervals quantify the uncertainty in the predictions based on the model's variance. Bayesian kernel ridge regression incorporates prior knowledge and uses Bayesian inference to estimate model parameters and uncertainties. Challenges and fixes. Challenge 1. Overfitting the model might memorize the training data, resulting in poor generalization to unseen data. Sample use case that resulted in challenge 1. When the model is trained with a large number of features compared to the number of samples, it might overfit the data. Fixes to challenge 1. Increase the regularization parameter alpha. Use a smaller subset of features, or use techniques like cross-validation to evaluate model performance. Challenge 2. Choice of kernel. Selecting the appropriate kernel function is crucial for capturing the desired nonlinear relationships. Sample use case that resulted in challenge 2. If a linear kernel is used for highly nonlinear data, the model might not capture the underlying patterns effectively. Fixes to challenge 2. Experiment with different kernel functions, such as polynomial or RBF kernels, to find the best fit for the data. Utilize techniques like cross-validation to compare the performance of different kernels. sklearn kernel ridge. Description: Kernel ridge regression is a non-parametric method for regression that uses a kernel function to estimate the relationship between input features and target values. It is a powerful technique that can be used to model complex relationships between variables, even when the data is nonlinear. Inputs: X, a 2D array of shape n samples. N features, representing the input features. Each row corresponds to a data point, and each column corresponds to a feature. Y, a 1D array of shape n samples, representing the target values. Outputs: self the fitted kernel ridge model. Steps: the model first learns a kernel function that measures the similarity between data points. Then, it uses this kernel function to compute the kernel matrix, which is a matrix where each element represents the similarity between two data points.